Okay, so you want to find when will host B receive the kth packet. Okay, so let's try to just simulate one packet first. So if we try to simulate one packet, you can think of it like this is your A, this is like your R, then this is your B, right? So for example, from A to R, the transmission rate is quite fast. It's 1 kilobit per second. So this would be something shorter, right? Then from R to B, there's a longer propagation delay. So there's like a longer line, but it is also a longer transmission delay. So something like this. Okay, gets? Now this is the first item, which is basically your first packet, right? If you can visualize the first packet, then that's already correct. Now the hard part is actually to visualize how the second packet will look like. So how would the second packet look like? Say, for example, if I send from A, it will go like this, right? Okay. But can it directly go this way? Cannot,
No,
because
you have
there's
to
another packet
wait.
sending. So the next packet, it can only start from here all the way up to this point. This is your second packet. Make sense?
Yeah, makes sense.
Makes sense, right? So then if I continue this idea, if I have a third packet, then it will also follow this thing. It will only be sent after the second packet leaves router R to B. Okay? Thus, if I view it from B's point here, if I view it from this perspective, you will see that this delay here, this is your propagation delay from A to R, right? This is your D prop, A to R. Then this part is basically your initial transmission delay from A to R. This part is your D prop from B to R. Then this is where everything gets variable. So you see that at this point, it is no longer dependent on the transmission rate from A to R, but now it's only dependent on the transmission rate from R to B. Okay? Understand this? Understand the idea? Okay, so let's count this. Propagation delay from A to R, this is 100 milliseconds, so 0.1. Transmission delay from A to R, that is 500 bits divided by 1 kilobit per second, that is 0.5 seconds. Then propagation delay from R to B, that would be 0.15 seconds. So this constant amount of delay, that will count out to 0.75 seconds. Now, this part here, one packet is 500 bits. Transmission rate of the R to B, that is basically 500 bits divided by 250, that is 2 seconds. So if I only have one packet, that is 2 seconds plus 0.75. I have two packets, that's 2 seconds times 2 plus the 0.75. So if I have k packets, then that will be 2 times k, the transmission delay from R to B plus 0.75. That's a constant value. So it should be A.
Yeah, it's pretty tough.
Yeah. Actually, this one is still easier. Wait till you see later on if you practice enough, right? There will be a question, something like, for example, if your A happens to be faster than the B. Now, this is tricky. Ah, you try this on your own later. I think there'll be a question about that also. Yeah. So this is why I emphasize in the class, right? You have to be able to understand how to draw these kind of diagrams, because that will help to settle nearly all questions that relates to transmission delay, propagation delay questions. As long as you know how to draw the diagram, how to visualize it.
Sorry, the D prop is from where to where? On
D
the
prop
right
is
side.
basically I mean how you read the diagram, right? Is, for example, if I have a diagram like this, right?
Okay.
So the width here is basically the D trans, right?
Yes,
So
the
even if I
transmission.
don't have, like, say for example, in the case that this is a magically sent item from A to B, this is basically the transmission delay. So say for example, if I can teleport 1 bit directly to the end, right? But in the real case, if 1 bit is sent here, it might only arrive after, say, a certain time. This is your first bit. So the amount of slant, amount of like shift that you do, this is your D prop actually. How much you shift this down, how slanted it is. That's your propagation delay.
Oh, the transmission delay is when it first sent to when it fully received, right?
No. Transmission delay is from when it starts sending to when it finishes sending.
Or when it finished the sending. Okay, okay.
Yes. But of course, if we assume that the bits will come together, right, since it's a packet, right, then the moment it starts arriving to the moment it ends arriving, it should be the same amount.
Ah, I see.
Okay.
Yeah.
You can't have something like this. This one is not possible for now.
Okay. Yeah.
Okay. Any questions? Can you explain how you get 0.75 and 2K again? Basically, once you draw the diagram, you will see what values are constant, what values are variable. In this case, if I simulate adding another packet, right, this 0.75 will not change, but it will only add another amount here, which is basically the transmission delay from R to B, right? Then if I go down again, then it will add another amount, which is the transmission delay from R to B again. So that is why the 0.75 is constant. In short, the depropagation, the dtrans, and the deprop from A to R, and the propagation from R to B, these three items is only a one-time payoff lah. It's like kind of if you want to start a business, what you pay first in the start. So like just a one-off payment. But the rest here depends on how many packets you have. So if you try to draw the diagram, then you try to add more blocks, then you will understand what changes, what remains the same. Okay. Okay. Anyone still have doubts about this question? If not, I'll move on. Okay. Now question 20. Question 20. Maybe Jason, you want to share any doubts about this question first?
This question, I don't even know how to approach. Because at first, right, I thought it will be the acknowledgement will just plus 100. So it will be 400. Well, let me reread the question. I did this some time back.
Okay. Okay. Maybe
Data.
let's try to solve this first, right? Let's
Mm.
see the green arrow here. For this green arrow, what will be the S, what will be the A?
So this will be plus 100 for uh, I think it's plus
What will be the
100 for S.
100? Why is it 100?
No, sorry. It will be 130 for A
130.
because the last known packet was 30, receive another 100. So you
Okay.
acknowledge back 130. And for
Okay.
S,
Recall that this is TCP, right?
yes,
So for TCP, what does the acknowledgement number mean?
it received the last known packet.
No. Acknowledgement number in TCP means that this is the expected next sequence number.
Okay.
Everything up to 29 has been received. I want to receive 30 next. Okay, that is your acknowledgement number in TCP. So in this case, if X sends an acknowledgement number of 30, that means it expects Y to send 30 next. That is for TCP. So you don't add another 100 here. What you add another 100 here is on the A side, because now X sends you byte numbers from 100 all the way to 199, right? That is 100 bytes. Okay, thus the next byte that you expect from X is byte number 200. That is when the A would be 100 plus 100, that is 200.
Oh, okay. I see.
Okay, remember, A acknowledgement number in TCP tells you the expected next sequence number that you should receive. So if A30 means X expects 30 to be received next. Now X sends 100 to 199, so Y will expect 200 to be received next. Okay, up to the first green arrow, okay, right?
Right.
Okay. So this question is actually a bit trickier because we don't actually have to handle this part. Okay, we don't actually have to handle this part. Plus we see here that when the second, when this second arrow comes in, okay, when this second blue arrow comes in, that will have sequence number s is equal to 200. Then A would be 130, right? So this green arrow here, this will contain s is equal to 130. Then your A would be, it will expect you to receive 300, I think. Yeah. Then if you go down again, this will be s is equal to 230, A is equal to 400. So this loss actually does not affect because all the blue arrows are able to come to Y. So this does not affect anything actually. Yes. And that'll be it. So this one should be option D.
Wait, so
Yeah. So
the X don't have to wait for Y to sort of acknowledge it. They can
which one?
just keep sending the next.
I mean, in practice would be great if you could acknowledge it, yes. But yeah, in for this case, then doesn't have to wait for it because of the diagram itself, right? Okay. Any questions? Okay. Then does it clarify your 3 questions, Jason?
Yep.
Yeah, but okay. Anyone has any other questions?
I have questions from the mock midterm paper.
Mock midterm paper? Which one is it? The one Florentiana sent?
Yeah.
Okay, let me check that. Okay. Okay, mock paper, which one?
1 and 2.
1 and 2.
Yeah.
Okay, let me see. This mock paper, oh yeah, this one is actually from the older curriculum, right? So also I think this one is for the finals.
Oh,
This one is for the
I skipped
finals
some
actually.
questions.
Okay, but some questions are of course relevant. Let me see. 1 and 2. This is number 1.
1.3.
1.3. Ah, okay. 10 packets are continuously sent over a 1 megabit per second link. Each packet is 1000 bits long and RTT is 10 milliseconds. What is the throughput of the link? Okay. Okay. Should I discuss this? So 10 packets are continuously sent over a 1 megabit per second. Each packet 1000 bits long, RTT 10 milliseconds. Now my question is, what is a throughput?
I don't really get what does it mean by the throughput of the
Throughput,
link.
right? So throughput is kind of like, you can think of it some kind of an average speed per se. How do I say an average speed? Say for example, this is your A, this is your B. If you want to send a file of size, say L bits, okay, from A to B, how long does it take? Say if it takes a total of say T seconds, then the throughput is basically just L over T, where T itself is a total delay. Okay, in essence, that is your throughput in its purest form. Okay, up to this point, clear, right? Throughput is just how many data you send, divide this by how long do you take to send from start to finish, your end-to-end delay.
Okay.
Now notice that when I say from A to B, it's not saying from A to B and back. That means the T here, the total time, is basically just the amount of time you have to transmit the whole file plus the amount of time for it to travel from A to B. So your throughput in this case is just your transmission delay plus the propagation delay. The total delay is just the transmission delay plus the propagation delay, your end-to-end delay.
Yep.
Okay. Okay, now we just need to compute what the transmission delay is. I think transmission delay quite obvious. That is your 10 packets times 1000 bits long, divide this by 10 raised to 6. That would give you 0. That will give you 10 milliseconds, right? So be 10 milliseconds. So this is your D trans. Now the question is, what is the D prop?
Is it 5 plus 5? Because
Yeah.
half of the RTT. Just one
Exactly.
direction. Right?
So
Okay.
this is the RTT, that means from A to B and back. But we only want to
Okay.
consider the propagation delay from A to B. So the D prop would be 5. Thus, we can now just divide the amount of data that we sent just now, which is 10 times 1000 bits. We divide this by the total delay, which is your 15 milliseconds, that is 0.015. Then you should get the option E.
Oh, okay. Understand. Then another question is question 10, 1.10.
1. What?
10. 10.
Oh, 1.10.
Yeah, 1.10.
Okay. Oh. A device D is used to connect a sender and a receiver. Transmission rates of the links between sender and the device and between the device and the receiver are R1 and R2. Ignore other types of delay. What is the end-to-end delay to send a packet of length L? Okay. So if we ignore the other types of delay, then yes. So this would be, wait, transmission rates of the links between sender and the device and the device and the receiver. R1, R2. R1 is greater than R2. No other types of delay. What is the end-to-end delay? How should I explain this? Okay, let me explain it this way. Say, for example, you have 100 people. Okay, or rather, never mind. Let's not consider 100 people. You have 100 different cars. Okay, I think that's easy. That one is easier. You have 100 different cars. Each of them want to travel from S to D to R. Okay.
Okay.
Now from S to D is a highway. Okay, you can think of it like, I don't know which expressway here is fast, but there are some fast expressway from S to D because your transmission rate is fast, right? But
Yeah.
when from D to R, this is like some kampong road. It's a very ulu road, the one that is very small. Okay. So D to R is a small road. That's your R2. So you can imagine the time it takes, right? For if you only have one car, then that is obvious. The time it takes is basically how fast you go from S to D. That's your 1 over R1 plus 1 over R2, right? Then quite obvious, right?
Yeah.
Now let's think of it when you have 2 cars. If you have 2 cars, both of them will travel fast in the first highway. But in order to start traveling from D to R, now this would be delayed by the first car.
Oh, yeah.
Right? So if you have 100 different cars, when you have 100 different cars, right, it would seem something like this. If I draw some kind of the diagram, this is your first car, transmission delay quite fast, then this will be slower. Okay. Then your second car, transmission delay quite fast, but it can only start after the first car leaves. After first car leaves D, right? So if I have a third one, that will be something like this. Then we'll only start here. Now we will see that actually you now have kind of a build up on the S to, on the second side, the R.
Yeah.
Okay. And if you see from the R's perspective, it's basically just the amount of speed it takes, right, to transmit the first car from S to D, plus now this will be variable.
Oh, okay.
Okay. So that is basically saying how long it takes for the first packet to go from S to D, plus how long it takes for the remaining to go from D to R. Because the rest here is actually kind of like hidden between. It's like, if you get what I mean, like if it's fast enough, then
But it's faster.
they just
Yeah,
they
okay.
just get queued in D. Yeah, so that is
the
the
one
reason.
over R1 is the initial time for the first car. Then after that, the L over R2 is the when they like queue up.
Yes, some
Okay.
kind of that, yes.
Okay.
Okay.
Then I have one more question for this paper. Question 5.
5.
Yep.
Okay. Two hosts A and B are connected via router. Link rate is 1 megabit per second. Propagation delay is 40 milliseconds per link. Maximum size of a packet is 1 kilobit and packet header is 80 bits. Suppose sender sends as much data as possible. How long does it take to send a 400 kilobit file from A to B? Okay, A to B. Link rate is 1 megabit per second. One packet can only contain 1 kilobit. Packet header is 80 bits. Okay, so for this, then first thing that if I see this question, right, if I try to do it right now, first thing that I need to know is how many packets are there, right? Because then you will have to multiply the amount of packet headers equally. So now you will send a 400 kilobit file. Each packet is 1 kilobit. So that means there will be 400 packets, right? Oh, there's a router. Sorry, I forgot there's a router involved. So there's a router. Okay, a link. Okay. Now 400 packets. Each of them contains 1 kilobit plus 80 bits. So that is basically 1080 bits per packet, right?
Yeah.
Then now we can compute the transmission delay for each packet. So from A to R, then the transmission delay that would be 1.08 milliseconds, right? Plus the propagation 40 ms. Then this will be another 1.08 ms plus a 40 ms. So something that looks like this, since we know that it's constant, right? From A to R, R to B. So this is like 1.08, then this will be 40. It's not proportionate, yes. Then this will be another 1.08. This is 40. Sorry, this is 1.08, 40, 40. Okay, after this point, clear, right?
Yep.
So if I add another packet, second packet comes in, then you just need to add another 1.08. I don't have to add another 40, 40 stuff again, right?
Yeah.
So if I add another third packet, I will add another 1.08. All the way up to I add the 400 packet, then I will add 399 1.08s on top of the initial this point. Okay, so in short, I can say that the amount of delay I can spend is just 1.08 plus 40 plus 1.08 plus 40 plus 399 times 1.08. This is the additional items I append. Or you can also think of it like just now the one I mentioned. These three are kept constant. These are variable. So it's something like 1.08 plus 40 plus 40. This is the constant plus 400 packets times 1.08. It's the same thing also. So that should, I hope that gives the answer.
Yeah.
Yeah. Hey, does it give the answer or am I wrong? Doesn't add up. How much is this? Let me check. Screw it. Forgot where I put my calculator. Okay, y'all can check this later. I lost my calculator.
Okay.
Any
I
other
got
questions?
confused with this because they said maximum packet size is 1 kilobyte, 8 bits. I thought it's inclusive of the header.
Oh.
Like, I think that part wasn't like very clear, so I'm not sure whether it's inclusive or not.
Oh. Oh.
Unless if they specifically state like MSS, then
Yeah.
then it's excluding. Yeah.
Hmm. Actually, this one I'm not sure. Later I'll ask them again. Sorry, for this I'm not sure also.
It's okay.
Yeah. Because yeah, you're right, you're right. This one is a bit ambiguous. If they say MSS or for example maximum data that can be carried or something, that would be easier.
Yeah.
Yeah. Let me ask the other TAs on their opinion also.
Okay.
Sorry. Yeah.
I have a question for the mock paper 2.
Paper 2.
Yeah.
Okay.
1.6.
1.6.
So I feel like I got a lot of true answers, so I still don't know how to.
Okay. Which of the following statements about IP header is true? Source and destination port numbers in the IP header determine which application on the receiving host will process the datagram. True or false? Why?
It should be. I think it should be true, right? Because
Port
port number
numbers,
is for process.
IP header. Is port numbers part of the network layer? No. Port numbers is part of the transport layer. So it is not present in the IP header. It is
Okay,
present in the
okay.
TCP or the UDP header. Okay?
Okay, yeah.
So this one is wrong because of the IP header. Second
Okay.
one, TTL in the IP header determines the time period which the source IP address is valid.
Yeah, I thought this one is true, because
So TTL
yeah.
field that determines whether the source IP address is valid. That one is actually more into the TTL when you have like say a DNS cache on how long the mapping is valid, right? But in this case, if there's a TTL field in the IP header, as what we discussed in the tutorial, it's basically how long should the packet live in the network. So it tells you the validity of that packet instead of the validity of the IP address. So say for example, if there's a TTL of, let's say TTL is like 3 minutes, that is what, 180 seconds. Okay, say a TTL of 180 seconds. If the TTL has been exhausted, then any node that receives this packet, whether it's the destination or not, they can safely discard it. So the TTL tells you how long the packet lives.
Oh, this is different from the lifetime, the DHCP server thing, right?
It's different.
That you.
It's different.
Oh, okay, got it.
Okay, so because this one is an IP header one, right? So it's a general version.
Okay.
Okay, maybe let's go through D and E first. D, checksum field in the IP header allows you. Actually, has IP fragmentation IP header been covered?
Yeah.
Covered already.
Yeah.
Okay. Oh, interesting. That's quite fast.
It's
Checksum field in
last week's
the
one.
checksum field in the IP header allows the receiver to check if the IP header or payload is corrupted. What do you think?
I'm not sure. I thought it was true also, because like checksum is just to check for errors. I'm also not sure what it's actually checking.
This one is actually, I would say this one is a bit ambiguous. Because of this question and because of this thing, right? Actually, let me check on this also together. Because if I recall, there are also like some points where the checksum might not actually include the headers or something like that, right? Something. Let me check. Lecture slides, slide 6. Actually, it's quite fast that they covered everything already in lecture 6. Last year, our lecture 6 was just routing protocols. Let me see.
He recorded a separate video for us to watch at home.
Oh.
Yeah, for the fragmentation.
Oh. Hit canvas. Where is it? Charts. Where's the IP header? Okay, yeah. So this is the IP header, right? Then, so this is where it gets tricky. So you see that the checksum here is what you call the header checksum. So this checksum doesn't check the checksum of the data. It just checks the header.
Oh, that's what's what. Okay.
Yes, that is why this is wrong.
Okay.
Which is why I will always recommend you all to print the lecture notes. Okay, so because it says this thing, it should not check whether the payload is corrupted or not. So whether the payload is corrupted or not, that is the purpose of your TCP UDP checksum, right? It's not the IP to handle it.
Sorry, what is payload?
Payload is the data.
Oh, okay.
Yeah, so I think payload is more like if you do like space exploration, right? Say if you have a rocket, right? Whatever the rocket is bringing, that is what you call the payload.
Oh, okay.
Yeah, so it's basically just the data that you are encapsulating. Okay, then this one is the last one. Protocol field in the IP header determines which link layer protocol should be used to transmit the datagram. What do you think of this? So this one, the problem is with this sentence. So if you like, I think look through the lecture slides or if you Google, right, you will see that the protocol field in the IP header determines which upper layer protocol that is used. So it is supposed to determine which transport layer protocol that is used, not the link layer.
Oh, okay.
Okay. Furthermore, you will also notice that in link layer, there's not much protocols. It's just Ethernet, right? So yeah, in this is supposed to be transport layer instead of link layer.
Oh, okay. So it just goes one up, right?
Yeah.
Okay.
So then the answer should be C. I don't have to explain why C is correct, right?
Yeah.
Yeah, this one is tricky. Even I forgot. Yeah.
Another question for 1.8.
1.8. Okay. Web server supports both HTTP and HTTP 1.1. So far, 100 clients have downloaded a web page from the server, which contains one HTML file, 2 images. Half run 1.0, half run 1.1. How many sockets have the web server ever created? I think this one has Florentiana scratches, right? So, any part you don't understand here? Is it because of the one?
Oh no, I understand the welcome one.
Okay,
I think I got 101.
101.
Oh, is it because 1.0 they close it every
Yes.
time they send something? Oh, so you have to create another socket again.
Yes.
Oh, okay, I understand.
Yeah. So one socket establish HTML, establish image, establish image. So just this one single host will ask you for three different sockets already.
Oh, okay. Okay, now one last question. Question 3.
Question 3 here. Okay. Two hosts A and B are 2,000 kilometers apart, connected directly using a link of propagation delay 800 bit times. Oh, bit times. Propagation speed of 2.5 times 10 raised to 8 meters per second. Then we have A sending a packet. Sequence of packets each is 100 bytes in size to B. How long does it take for B to receive a packet? Yeah. So what's your concern here?
I don't know what you mean by 800 bit time. What does it mean by that?
So this one is kind of has the lecture covered this?
Too sure. I'm not too sure.
Yeah. Because if the lecture has not covered, then likely it will not come out. The reason why is because, as far as I'm concerned, this is some week 11, 12, or 13 topic. I forgot which which week. But it's a topic there.
Oh,
The
okay.
sliding window thing.
Hmm?
Are you talking about the sliding window?
No. But let me just give a spoiler of my slides, right? Yeah, bit times will actually be bit times is actually going to be discussed in week 11 as of my slides. So bit time is basically the time to transmit one bit. So just 1 over the transmission
Yeah.
delay.
I don't think that was covered.
Exactly.
I
So
think
if it's not covered, then
okay.
likely you will not touch this yet.
Oh, okay, can. Yeah, that's all. Thanks.
Okay. Yeah. Okay. Any other questions? We have 7 people here. 2 people has asked questions. The rest questions. Anyone has questions? Which papers have you all tried? Perhaps have you all tried the 22, 23, 23, 24? Okay, sample paper 2, question 18. Let me share. Oh, you can call me Jason, by the way. I've people calling me TAs, tutors, like just call me Jason, it's fine. Question 18. Suppose 2 hosts are connected by a direct link of 1 megabit per second. Stop and wait protocol is used to transfer 10 packets from the sending host to the receiving host. Each packet is 1000 bytes long. RTT is 24 milliseconds. No packet is lost or corrupted. What is the throughput of the transmission? So this one should be similar to the previous question. So now you have 2 hosts, A and B. The link here, the transmission rate is 1 megabit per second. Then you have an RTT of 24 milliseconds. So if the RTT is 24 milliseconds, this one you have to convert back to the propagation delay first. That's basically half your RTT. So that is 24 milliseconds divided by 2. That will give you 12 ms of propagation delay, right? So that is just for this point. Then we now have to calculate the transmission delay also. So the transmission delay that would be given by, that will just be, you have 10 packets. Yeah. So the transmission delay, that is 1000 bytes times 10 packets times convert from the bytes to bits. Okay, that's the trick here. So if the convert from the bytes to bits, that means you times 8. So then the D-trans is 80,000 divided by your 1 megabit per second. That will give you 80 milliseconds. Right. Yeah, so that's your transmission delay, 80 milliseconds. So if we now consider the throughput, which is basically just how much file you send, data divided by what is the end-to-end delay. So the amount of data we send, just now we sent 80,000 bits, divide this by 80 milliseconds plus 12 milliseconds, then that should give you sorry. Yeah. Then that should give you how much? 80,000 over quite big. Check. Did I explain this wrongly? Okay, this might be okay. I might have explained this wrongly a bit, but this might be the case where this might be the case that we have to consider the RTT instead of the propagation delay. Yes.
But which under what circumstances do we then use the full RTT instead of like dividing it by 2 to use the propagation delay?
In that case, then this is my hypothesis. Yeah, this is my hypothesis. Need more questions also to verify. But that also depend on what the question asks here. If it says the throughput of the transmission, then it might refer to actually just when it starts sending up to when it finish receiving, something like that, for example. But if it case, for example, what is the throughput of the link from A to B, then that is just one single, that will be just one single direction. That's my hypothesis. Yeah. Oh, sorry, I'm wrong. sorry for this. I forgot the key part.
Is it because it's stop and wait? Yeah.
Yes, I forgot this part. So because of the stop and wait, you have to receive the ACK first. Yes, I forgot that. So still the same thing, still the same throughput. However, now this will consider the RTTS because of the stop and wait. So thus the propagation delay would be, this would be dprop of the data plus the dprop of the ACK itself, which is your 1/12 milliseconds also. So then that would be yeah, that would be, this is 80 ms plus, this should be 24 ms, right? Then that should give the answer. Is it right? Check. 0.04. Is it?
Yes. So the 24
24
milliseconds
ms
is
times 10.
because of
Yeah, times
the
10.
data taking 12 ms and then another ACK flag taking 12 ms.
Yes.
Oh, okay.
Yeah, so basically just this item, this item, this item, this item. Before the second item can be sent, the first item has to be sent first, right? The first ACK has to be received first. That will incur the delay. So propagation delay here would be, this is 12 ms times, we have a total of propagation RTT here is 24 ms times 10 different packets, right? So that will be 24 times 10. Thus this will be 80,000 divided by 80 plus 24 times 10. Then that should be the answer. 250. Yeah, but in essence, the throughput is just this thing over the end-to-end delay. Okay. Questions on this? Yeah, this one is tricky. I got caught by this. Any other questions?
One question from the Kahoot, question 17.
Okay. Kahoot, let me
I
open
can't
Kahoot first.
derive the link.
Yeah, I need to download. Shit. Please don't tell Prof. Leong I use his photo. Which question?
Question 17.
17.
Oh, the fine print.
Oh,
I know how
okay.
to work it out.
Okay. A sends 5 packets to B using TCP. Within 100 ms, B receives 5 in-order packets. You have a copy of how the fine print works, right? Or rather the lecture slide also. Have you seen that?
Yeah, I saw it.
Okay, so I'll just repeat first. in essence, if you receive an in-order packet, right, it will decide either two things. If there is no packet that is currently waiting for ACK, as in there's no packet that is delayed, then you have to delay it, right?
Yeah.
Delay by 500 ms to wait for another packet. If there is already a packet that is being delayed, so if you come, then there's somebody already in there, right? Then what happens is this will directly send an immediate ACK. Okay, so we now visualize this. This is your A, this is your B, right? So A will send one packet here. This packet, when it reaches B, it will see that there is no other packet that is currently being delayed. So it will now wait for 500 ms until someone comes. Okay, which miraculously we have another packet that comes within that 100 millisecond, right? So that is like much less than the delay that is supposed to be waiting, right? So this second packet comes. When second packet comes, this will send what we call the cumulative ACK directly. So it will ACK both the first and the second packet. Okay, so this is one ACK sent.
Okay.
Okay, then third packet comes. Third packet comes. This will delay for another 500 ms. Then fourth packet comes. What happens? This will send cumulative ACK, another one additional ACK.
Yeah.
Fifth packet comes. It will wait 500 milliseconds. Apparently no one comes. So in this point, it will just send an ACK. So then we have 3 ACKs.
Oh, okay. Good.
Yeah, so the fine print is basically because of this immediate ACK. It doesn't wait another 500 ms. Okay. Any other questions?
Regarding the accumulative ACK, right? I think it was mentioned somewhere that they say the TCP protocol in general is cumulative ACK.
Yeah.
Like does cumulative ACK, right? And what about the time where they use the selective repeat for TCP? Wouldn't that mean that it's not like cumulative because each packet like will have its own like ACK or like timer, that kind of thing? Yeah.
Okay. So you're saying in the case that it'll be more selective repeat-ish, right? I
Because
mean,
there's two ways they can go about, right? Like the go back end and the selective repeat. So like I guess in general, if it's go back end, then it would just make sense, like just cumulative ACK. But in the case where they use the selective repeat, it's still under TCP, right? And then it wouldn't make it cumulative ACK anymore, right? How will you define it?
so for this case, it's basically, it happens that if they are receiving it in order, right? But if it happens that something is like out of order, then you have to refer to the fine print again. Yeah, because if there's an out of order segment, then this is what it will trigger, right, for this current case. Although it is arguable that if it's out of order, then TCP does not actually specify, the initial RFC does not specify what you should do, right? But
Right.
so you can either buffer it or you can discard it. But in that case, then you will have to send a duplicate ACK in both cases.
So only in the case where it's in order, everything is there, then you have like the 100 millisecond, the 500 millisecond, what's it called? The cumulative ACK.
Yes. So in the
I see.
case that, for example, an out of order segment comes in, right? Then you can either discard or you can buffer it, but you will have to send the expected byte item. So this is just my guess, right? I'll have to confirm this again later on. But for example, if say one packet is currently being delayed, okay, so if it happens that an out of order segment comes in, then we'll just send an ACK for the previous one, technically.
So you wouldn't wait for like 500 milliseconds, right? So suppose like 1, 2, 3, is there's like 3 total packet. So they receive
Yes.
1 and then they receive 3. So they will just straight away send 3, right? Or would they still like wait and whatnot?
There's one that is 3, for example. So there's 1 coming. This is 1. So 1 will wait, right?
Yeah.
Then 3 comes in. 3 comes in, then they should just, when 3 comes in, we see that actually it will never invoke back the waiting part again, right? If 3 comes in, it can either be an in-order segment, out of order segment, or something that fills the gap, right? So in
Yes.
either 3 of the cases, it's actually immediate ACK. Right.
Okay, I see.
In either of 3 cases, it's always the immediate ACK. So then you just, in this case, it will send, in this case, then it should send ACK of, this should be ACK 2, right? Because it expects 2 to come next. Yeah. But whether you want, so you have to send an ACK 2 here, but whether you want to keep the 3 or discard the 3, that is dependent on the programmer.
Oh, so that's where the go back end and the selective repeat comes, huh? Is it?
Yes.
I
In
see.
a way, yes. But on how you handle the ACK, it's already specified by the RFC. Just to handle whether you want to discard the packet or not, that is dependent on the programmer.
Okay, can.
Any questions?
To listen. Because I already done the 2 paper that was uploaded.
Okay.
Is there any solutions for the 22 and 23 paper?
Oh, did I not upload this? Oh no. Okay, wait. I upload first. Let me just move from my last sem's Google Drive. Copy, paste. Okay, uploaded.
For the 23, 24 don't have.
23, 24, I don't have the solutions.
Okay.
Because it was only published in the Piazza for last sem.
Okay.
However, I do have my own solutions I will share later. This is my solutions. Which is verified with the last year's Piazza also. Because you will see later on, I think in week 8 tutorial, the week tutorial is reserved for discussing the midterm, right? So then last sem I had to do the midterm also so that I can discuss.
Do you perhaps have any more interesting questions that you think will be good for us to know?
I do have some. Let me see. Because last sem my students asked me quite a number of questions. Let me see if I still have access to it. Yeah, let me see. Last sem was a fun sem. I learned more about TCP last sem than when I took the sem. Where is it? I think I do have some students asking me. Which one is it? Is this guy? No, not this guy. Including actually there's one that I should share. Where is it? Yeah, give me some time to try first. Give me some time to search for it. Meanwhile, you can ask any questions also. Shucks, I forgot what's the student name. So bad. Yes. Oh yeah, this is fun. Wait, I found a question. Eh, not this one. Never mind. What is this? Okay, let me go to the sample paper. Let me ask you a quick question. Yeah? Question 17, same question. If I switch the question around, if the transmission rate here is 250 bits per second, and this one is 1 kilobit per second, what will be the equation? This one is fun. So if I switch the transmission rates of link 1 and 2, what will be the answer? Y'all can try this. Meanwhile, if y'all have any questions, feel free to ask. I'll discuss this in about 3-4 minutes when y'all try. It's not 2 plus 0.5k. It's not. This one is I think a much more fun question than the previous one. I think the constant side is also incorrect here. Maybe another 2 minutes, then we'll discuss it. I felt like if you understand this question, right, then any question that relates to the propagation delay, transmission delay, that will be easy already for you all. It's like the pinnacle network question, I think. Okay. Anyone else has an answer? Jason, did you give it a try? You're the one asking for an interesting question.
I need to brush up on all the delays and stuff. I can do the theory-based questions, the calculation questions I have yet to brush up. Do it tonight.
Okay. Okay, so here is how I always solve this kind of question, right? You need to always try to draw, then try to imagine how it flows up. So let me just draw this out first. Let us draw the case of only one packet. Okay. In the case of only one packet, you see that the transmission rate for the for the A to R, the first transmission rate here is larger than the transmission rate is smaller, right? So then the transmission delay would be greater. Thus, if I draw the first packet, this is how it would look like. This is the first packet. When it reaches the B, that will be quite fast. Okay, this is how the first packet should look like. Questions on this? I think this one is easy, right? So let me just color this up for better readability. This is the first packet. Now let us imagine if a second packet comes in. If a second packet comes in, it will be sent back to back after this, right? Correct. So it will be sent here. My question is, can you start sending like this? Can you?
The packet not come in fully.
Yeah, exactly. You cannot send it like this. So the second packet will have to flow like this. Okay, so this is the range of your second packet. Now you will see that on the right side, there's a gap. This is just an empty gap. So this is where it gets interesting. So now if I have, say, a third packet comes in, third packet will also have the same gap, right? So this is the third packet. This is how it will reach B. Yes. Now let's try to calculate. So everything up to this part would be constant. So we see here that this is the propagation delay from A to R. This is the transmission delay from A to R. Then this will be the propagation delay from R to B. Okay, easy, right? The three constant values are here.
First, then propagation. Isn't it transmission first, then propagation?
I mean, if you look at from the right side, then there will be propagation first.
Oh, okay.
If I look from this perspective, right? This is me. Because if I look at from the right side, then it's just transmission delay all the way, right? Yeah. So if I try to look at from the right side, If from the right side, then I will see here that it's a propagation first, then a transmission, then a propagation again. So I'm looking at from the B's perspective. I don't know what happened. Okay. Okay. Now the next part here. So before that, I'm too excited. Okay, so this would be 0.1. Transmission delay from A to R, this should be 2. This would be 0.15, right? So the constant values, this should be 2.25. That's the constant items. Okay, up to the constant part clear? It's basically 0.25 plus the transmission delay initial one. Okay. Now comes the variable part. The variable part here is if you send, say for example, say if you send like one packet, then it will go this way, right? Then if you send, say, 2 packets, it will go this way. If you send, say, 3 packets, then it will go something like this. Okay? So how do I calculate this part? If there is 1 packet, then that is just the delay from B to R, from R to B. If there's 2 packets, how much do I shift down here? This is exactly the transmission delay from A to R actually. You see the width here from the moment the second packet, the first packet comes up to the moment the second packet fully comes. That is exactly the transmission delay of the first one. Okay, this part is where it gets tricky. So we see if k is equal to 1, that is just basically the trans of B R to B. If this is equal to 2, then this will be, say, d trans of say from R to B plus the d trans of A to R. Then if k is equal to 3 here, we see that we now have to wait 2 times, right? So that is from R to B, the last one here, plus the amount of weight up to reach the last one. So that is equal to 2 times the d trans of A to R. So in essence, the amount of delay here is basically the propagation delay from A to R plus transmission delay from A to R plus propagation delay from R to B plus transmission delay from R to B for the last packet, because we don't have to wait another one here, right? It's not empty gap. Once the last packet reached, done. So that is the transmission delay from R to B plus k minus 1 times the transmission delay from A to R. Or this part here, I can actually combine these two, since both of them are transmission delay of A to R, right? So that is basically just saying d prop of A to R plus d prop of R to B plus d trans of R to B plus k times the d trans of A to R. So that should be 0.75 plus 0.75 plus how much? Forgot. Yeah, so this would be actually similar again to 0.75 plus 2k. Yeah, should be same.
Damn, it's over.
Yes. So this should be the same also.
They wouldn't make it such that it will be like pipeline, right? And then on the right side from R to B, you can just send straight. That kind of calculation seems like pretty complex.
I say it might be in a case. Yeah. This one is quite tricky.
Oh, also right, if they don't say pipeline, right, it's always assumed to be store and wait, right? Like store and forward for this type of router.
Router is always store and forward.
Or it's always store and forward.
Yes.
Then the case where you'll be there's like the pipeline that will be for switches, is it? Oh, I recall like the first tutorial, like second tutorial, there's a comparison between like
no.
store and forward one.
There is a difference of store and forward and stop and wait. Opposite of stop and wait is pipeline.
Oh, okay.
Right. Stop and wait is one by one, right? This is stop and wait. Then pipeline is na 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 na.
Right.
Okay. Store and forward is basically irrelevant with both of them. Store and forward is this is a packet. Before it can go to B, in the router, it has to be reconstructed first in its full form. Then it sends to B again. So don't confuse store and forward with stop and wait. These are two different things. Stop and wait is before you send the next packet, you receive the ACK for the first packet or the previous packet. Store and forward is before you proceed from the router to the end, you have to reconstruct the whole packet first in the router. So in this case, actually, this one is more of a chapter 1 item where we don't discuss about any of the transport protocols yet. So you see that there's no ACK in this form, right? So it's only basically if I want to send data from A all the way to B, but it passes through R. So it has to be reconstructed at R first before it can forward to B. So it doesn't have anything to do with stop and wait or pipeline.
I see.
But yeah, for this kind of questions, you can assume that there should not be any form of waiting on the A side. We just send directly. And unless stated otherwise, you assume that the router has sufficient buffer.
Okay.
Any other questions? I'm quite glad that you all have started to do the past papers. Last sem when I opened the consultation on reading week, no one did because maybe the exam was on week 8, so no one actually handled the past papers yet. I think by far, as long as you all are careful enough to read the questions, then should be fine, I guess. Any questions? Okay, if no questions for now, let me just share a bit. Some perks are y'all get an hour earlier to know something. So here's what I can share with y'all. So remember that I have this like my personal midterm answers for 23-24. I wrote down a digital version of it also. So y'all can head over to this website that I created. Okay, is it sharing? Yeah, it's sharing. Yeah, so I created this website. It contains 3 different practice paper 1, practice paper 2, and the latest midterm. Contains like the how I solved this basically. So y'all can check this later on also. Actually, right now y'all can also check. I'll share in the group later after the consultation. If y'all have anything that probably is unclear, you can also ask me right now. Yeah.
Thanks for the resource. Oh my god. Do you have midterms to prep also?
No, this was from last sem. This is
like
last sem.
you personally.
Oh, I mean, I have midterms. I haven't touched. I procrastinate on that. It's fine. I'm more concerned about my assignments rather than my midterms. Yeah. Yeah, some of them I also include like some pop-ups also on like what kind of common mistakes, important things to note. Yeah. Hopefully can be helpful. But it's only these three. If it's outside of these three, then feel free to just chat me or can ask the group also. Yeah, that is it. I think for some of them, some of the diagram wise, I'm a bit lazy to put the diagram. So y'all can ask me later on that also. Last time's paper, I think should be quite straightforward. Oh, there was this question that is quite tough also last sem. So if y'all are interested, y'all can also try to do this. Shucks. This one. Question number 25 is fun. This one is fun. So question number 25 will actually test you how you understand go back end and selective repeat. I think like some past papers also have this kind of question, but the one on the midterm last sem was more challenging, I think. This one is slightly challenging also, but this one is more tricky than challenging, I think. Three. Any questions? Initially, I planned the consultation to be like ad hoc stuff. If you have any questions, just ask. If no questions, then if you all want to do something else, also can. It's not really like a fixed time, 2 hours that I'm going to give another lecture or something like that.
Yeah, the question 23, right? How you even approach
This one.
yeah? How do you approach the question like this? The first time I see a question like this.
Point graph shows a sequence of TCP segments sent from a TCP sender Alice to a TCP receiver board. Each stop represents a TCP segment. Suppose no segment is corrupted. Alice sends data segments, Bob sends ACK, further assumes that Bob discards out of order segments. After receiving segment labeled F, Bob immediately sends out the ACK segment. What is the acknowledgement number in this ACK segment? So basically, it's just showing that it's an order from A, B, C, E, D, G, F, right? It's supposed to be that way, right? Increasing sequence number. But some of them are out of order. Say D here is out of order, then your F and your G is out of order, right? So the question is, what do you do in that case? So it's like, this is like kind of
discards
a
both.
time. No?
So you discard both the D and F, right? Since they say Bob uh, discards out of the order segments.
Mhm.
So,
So
so
what would be
in
the
that
ACK number?
case, it should be C, the 600.
Why is it 600?
That's the last receive in order segment
What is the last received in order segment?
from like the C, right?
C is, sequence number C is 300, right? Not 600.
Oh shit, that's the millisecond. All right, yeah, 300, yeah. So it should acknowledge 400 because it's is it 400?
What happens to E? E is in order, right?
Oh, but D is out of order.
D is out of order, yes.
So it
D is out
should
of order.
so you should take out both E and you should discard both D and E, right? No?
I see, yeah. A comes in, accepts, right?
Yep.
ACK 200. B comes in, accept, ACK 300, right?
100, yes.
C comes in, accept, ACK 400.
400, yes.
D comes in, discard.
But
ACK
yeah,
what?
D 400.
400. E comes in, Accept discard?
Discard? Because it haven't received the D, right?
What
Or
is
should it?
the sequence number of E?
E at this point is 400.
400. So E is supposed to come first before D.
Huh? Really?
So A, B, C, D, E, F, G, right, is in increasing time, not in increasing sequence number. So if this happens to be all in order, right, it should be A, B, C, E, D, G, F. If you want it to be in order.
Right.
So E is in order. That's the, yeah.
Oh,
So
so we
E
don't
is
follow
supposed to be,
the alphabet? What?
sorry?
We don't follow the alphabet?
No. The alphabet here is basically in increasing time, not in increasing sequence number.
Right.
Right. So when E comes, E is your 400. Your receiver expects 400, right? So now the 400 comes. So accept
Right.
this. ACK, 500.
Then
F
comes
comes in,
D. Oh,
out of order. ACK, how much?
500, 500, ACK 600.
500, right? Because it's out of order, right? So it takes the previous one. F is
Oh,
out of
okay,
order.
okay. I think I see. Okay.
That should be this.
Fine. Then that comes G. Oh,
G comes will also be discarded because out of order. ACK 500.
hmm.
Unless there's another D comes, then this will be accepted. Then there'll be ACK 600.
Oh,
Yeah.
oh. So you start off with like A, right, is 200, and because B is on 200, we know that that is in order.
Yes.
Ah, okay. I see. Shall go and try this later.
Yeah.
Sorry, just the question. I still don't get why the transmission is first. Because isn't it like processing, then after that queuing, then transmission, then propagation?
For which
So
question?
why is the question 17, practice paper 2?
Practice paper. Sorry.
Oh yeah, this one. Yeah.
Sorry. Yeah.
Yeah. Why isn't it transmission first? Because isn't it processing, then queuing, then transmission, then propagation? So why is the propagation first in the timeline that you draw?
It's this one is not in the order of how do I say it? This one is not the correct order, but rather it's more like it's easier to count from up to down. You're right that in the end it will be like, say, you have the processing, queuing, then transmission first before the propagation, right?
Yeah.
But if I look from this perspective, if I go up to down, right, then it's easier for me to count up to down first, rather than me having to mix match. I mean, you can do a mix match also, but less systematic to count. Say like this. Let's try to read from this perspective, right? Say this is you. You are here, right? Okay.
Yep.
You are here. This is you. You are looking at, say, a group of people. These people are all queuing, right? Okay.
Yeah.
They're all coming to you. From the moment that you start seeing these people coming to you, up to the moment the last person comes, what would be the delay? So the delay here would be, if you are in the receiver side, that means you will have to wait until the first person comes to you. Then how long does the queue takes? Right.
Yeah.
So that is essentially what I'm doing here. It's on the receiver side. I will have to wait for the first bit to come. Then that will take the D prop first, plus the D trans, because it waits in the R, right? Then it will take another D prop here, then it will actually arrive. So it's like if I see from the receiver side, okay, the first bit will start to come to me. Then the first bit will pause in the router first because he has to wait for the last bit to come to the router. Then you can start moving again. That is when I say from the receiver side, if I just count it from up to down, that will be easier for me to count.
Wait, I don't
So
really
to clarify again, you're right that the order is wrong here. However, in the end, we are doing a sum. We don't care about the order of the delays as long as we count the total delay. That's why even in the calculating of say throughput, if I interchange the transmission propagation delay, whoever comes first, it doesn't matter, right? In a sense, as long as the amount here is correct, it should not overlap each other, and then the respective links are correct also lah.
Okay.
Has the lecturer discussed about the scope of the midterm, like up to which lecture is it covered?
I think it's until last week, man. I think lecture 6.
Oh, the lecture set up. Because
The IP, I believe.
the week 7 tutorial might not come in to the midterm. But yeah, in case that y'all wanna, if y'all FOMO also can try to read the week 7 tutorial also. It's not that hard.
Oh wait, sorry, back to just now the question again. Because they said host A starts sending the first packet at time 0. That means it already transmitted, right? That means you don't include the
Yes.
transmission delay, right? So straight away propagation.
Sorry. Transmission delay is the time it takes to from the moment it starts sending the first byte up to the last byte, right? Correct?
Transmit onto the link, right?
Yeah. So if it says start sending the first packet, that means it's basically start sending the first bit of the first packet at time equals 0. So then you have to account the transmission delay lah, after the last bit of the first packet leaves.
Oh, okay.
Okay.
Alright, I guess there's no questions.
Maybe I'll just wait around until, or I guess if you have any popping questions.
First, thanks for the consultation today and the
No worries.
resources. Thank you so much. Bye.
Thank you. Xavier, you have any questions?
As of now, no. Do you think the midterm papers you post are like enough?
For now should be enough, I guess, if you fully understand.
Okay, I guess I'll continue doing them. Can I message you if I have any other questions?
Yeah, sure. Feel free.
Okay, can. Okay, can. Thank you.
Thank you.
Okay, bye bye.